So when we say beta matters, but it doesn't matter, if we see what happens for a transistor with a different value of beta, we can go to this equation and plug in different values of beta. So if beta was equal to 50, which would be a particularly low value, beta would be a particularly low value of beta. Sorry, 50 would be a particularly low value of beta. And we plug it into this equation. Instead of 9.2, we're going to get 9.1. It's supposed to be a 50. If beta is equal to 200, if it's an unusually large value, our emitter voltage is equal to 9.25. So the point of all this is to say, what is mattering in this is that beta is big, and so beta over beta plus 1 is approximately 1. It's 0.99. It's 0.99 for this one. It's 0.98 here. It's 0.99 something here. So that's what I mean when I say beta doesn't matter. And as I think I put in an email or something, this is a quote from Horowitz and Hill, like any circuit that requires a particular value of beta is a poorly designed circuit. You can't assume a transistor is going to have beta of 100. If you pull out different ones out of the box, they're going to measure, within, probably within a factor of 2, but 80, 150, like those aren't crazy numbers. And it also does things like change with temperature, and that can create problems also. So anyway, you can rely on beta being in the ballpark, but not being 100 and not 110 or 90 or things like that. Okay, anyway, so that's how we analyze this. We'll stick with our beta equals 100 answer and know that even if beta changes, it's staying within this by 1/10 of a volt. Okay, so we found the emitter voltage. Why did we want to do all that? Okay, so here's one thing to notice. If we look at what the actual values of the current is, the current through the emitter, the current coming out of here, if VE is 9.2 volts, IE is 9.2 over 1 kiloohms, that's 9.2 milliamps. So we're getting a 9.2 milliamps of current through our load, or 9.2 volts across our load, however you want to think about that. What is our base current? Remember, our base current was equal to 10 minus this voltage, which is VE plus 0.7. So 9.2 plus 0.7 is equal to 9.9 divided by our 1K resistance. So this is 10 minus 9.9 is 0.1 volts divided by 1K gives us 0.1 milliamps. So we're only asking 0.1 milliamps of our voltage source, and we are getting out 9.2 milliamps because that is what our transistor is doing. Where's this other current coming from? Well, it's coming from the collector from this 15 volt power supply. So you need something else to supply this power, but the transistor is assuring that it gets to the load in a way, proportional to the input. And that's what we're going to talk about next year. So we did this analysis assuming this voltage is 10 volts. So what happens if we change this value of 10 volts? So all of our analysis, I've kept this up here. If we change this number to, say, 11 volts, let's just go with that. If we change this number to 11 volts, in this equation, we don't have 9.3 volts at the, this 9.3 came from the 10 minus the 0.7 volt drop. So that's going to be 11 minus that 0.7 volt drop. So this is going to be 10.3. And this is going to be 10.3. And when we solve this for VE, we're going to get something like roughly 10.2 or something around there. So we increase this by a volt, and VE also increases by a volt. It turns out these two are always going to be about 0.8 volts apart, 0.7 or 0.8 volts apart, for a whole bunch of values of this input. So in other words, We'll write this down. VE stays 0.7 to 0.8 volts below the input voltage. And a whole bunch more current gets supplied here than is drawn from the source. So it stays that much below the input voltage. Current is from the plus 15 volt supply. Okay, so this is why this is called a voltage follower. Because for a whole bunch of different values of the input to this circuit, the output, which I can now label, VE is our output. Our output follows the input. Now it doesn't stay exactly where it is. It stays, a constant 0.7 or whatever volts below it. But that is a lot better than we were doing, right? So if we think about what we had before, when our load was just directly connected to this, and this was 10 volts, we got 5 volts across the load. With this, we can get 9.2 volts across the load, and if this goes down, that will go down. If this goes up, that will go up. That's useful. So this is essentially an amplifier. You have a voltage signal, and you are outputting basically that same voltage signal, but with much more current. So you are amplifying the current that this weaker source provides to a load. Okay, there are some limits to this behavior, and the limits are this. This following only works it only follows as long as the input voltage is less than 15 volts. So if our input goes too high, we definitely can't, like if this is 16 volts, our output is never going to be able to go above a couple tenths of a volt below 15. So no matter what's going on over here, this cannot go above 14.8 or something like that. And so we're never going to, we're not going to be able to follow voltages that go too high. We also can't deal with voltages that are too close to ground. So it only follows if Vn is greater than about 0.7 volts, because that is what it takes to turn on this base emitter diode. So you need that base emitter diode to be on in order to have this current amplification effect. So if we're to graph the behavior of this follower, it'll look something like this. So if this is our voltage, we'll say this is our voltage input versus time. We'll make it a big sine wave or something. And let's make this crazy. Let's say this is like a 20 volt sine wave or something. So our input voltage, we're making big just to show that this is not going to be perfect. So our output voltage is going to be falling below this up to 14.8 volts, where it's going to be flat and not be able to reproduce it. And it's going to be 0 where this thing is below 0.7 volts. And where this is backwards, it's also going to stay 0. It's going to stay at ground. So this is not, this is not a particularly good follower for all possible voltages. But if you have something, that is positive and staying, between 15 and 1 volt, this is going to be able to follow it, exactly, just being 0.7 volts below it at every point. So that's pretty neat. You also can get it to follow negative voltages. You just have to change this from ground to some negative voltage, right? So if this is minus 10 volts, then our output could go all the way down, closer to the negative direction. Because if this is negative and V out is negative, as long as this can stay below this input voltage, so that we have this 0.7 volt drop, it'll still work. So in other words, if this is negative voltage and the input is 0, we're still going to get a 0.7 volt drop, so we're still going to be able to follow the voltage. All right, so yeah, voltage follower, very simple circuit to analyze. Lots of applications. You can, in principle, you could use this for something like amplifying an audio signal, as long as you had things biased right so that it could follow the right voltages. You could use a small weak voltage signal coming from a CD player or something like that, put it through this voltage follower and have it drive a larger current through a load that was a speaker or something like that. There are lots of other examples anyway, but this is a good simple example of a very practical transistor circuit.